recording. So the first is before the class begin. So I want to talk about a Kaggle competition, machine learning competition I'm currently in. So we still have two potential spots in our team. I mean, currently, so let me introduce Kaggle first. So we'll do our final project on Kaggle. Kaggle is basically a machine learning competition platform, and it's hosted by Google, and you have all these fancy machine learning competition. So we'll do the in class one. I mean, these are some so these are some competition I organized in the past, in my past institute. So we should have something similar in this semester. So we'll compete with our classmates. But I want to advertise this Jane Street one. So this is the one I'm currently advising like several students. So currently we still have two potential spots. So I'll send the link in our Canvas page. If you're interested in participating this competition, by the way, Jane Street is a very famous hedge fund. So, for example, it says buy low, sell high. It sounds so easy, but normally, sometimes we ended up buy high, sell low. You know, so this is a competition, and the coolest fact is after the competition ends, our model will be put to the test against the real market data from this year's February to this year's August. So if you can, so here we have a merger deadline. So if you're interested, and you can submit a solution before the merger deadline, and you are interested in joining our team, you can send me a personal email. So so currently I think we are very high on the leaderboard. So we are like 27th. I think I submitted a solution last night. So, but we are probably overfitting the leaderboard. So, this ranking may not represent our real ranking. So, for example, you guys will see. So here, this in the money. It means if you are in this placement, Jane Street will, you have this lot of $100,000 prize money, and winner will get those prize money. So, and this is for the Kaggle competition. Like I said, if you are interested and you work out by yourself and can submit a solution before the merger deadline, I mean, we can form up a team and we can learn something new together. So let's begin. So let's begin our lecture 2. In lecture 2, so we'll be mainly dealing with, oh, by the way, before lecture 2, I do want to start a poll. So the poll is, you have noticed there is some background music, right? So because I live in my basement and there's a huge heater beside me. So here's a poll. It's totally anonymous. So if you like the music, you can hit like. If you hate the music, you can choose no thanks. Okay, so I see majority of says it's okay, but just a little less louder. Okay. So I dial the volume to be 60% of the original volume right now. So now let's begin our class. And the first one is the workflow. So where we use the optimization technique we learned from last semester. The workflow. So first is we choose our model. The next one is we formulate the loss function. Again, the model is some complicated non-linear function. The loss function characterizes the difference of our model's output with the ground truth. And next is the train, and next is we validate. Okay. So this is where we use our optimization. And today's lecture, we'll talk about some of the model and loss function. So the first model we'll learn is called a neural network or multi-layer perceptron. Okay. And we'll see many other models throughout this semester. So other model includes, for example, so we'll learn some of the time series modeling. Normally we'll use something called LSTM, and it's called a long short-term memory. Okay. So, and we may learn some other model. For example, right now there is a state-of-art model called a transformer. So for example, in the famous language translation model called GPT-3, which has 120 million parameters. So, and it's based on transformer. Basically, you give this GPT-3 a German sentence and it will translate to English automatically, and almost like native, like translators, like human translators. And we'll learn some of these other models and using some cloud GPU resources, but not on our own computer. But these are some possible potential topics. But this is what today we'll do. Okay. So let's first formulate the problem. Let's see what normally a neural network is trying to model. So for example, if we have some sort of the data, I'm drawing like a high dimensional picture on one dimension. So one axis represents like Rn, the other represents the function, like the value. So what we have is we may have all these, sample of the data. So these are some, data points. So for example, let's say xi, yi. So xi is in Rn and yi is in R. And what we want to do is we try to do a data fitting. We try to find a nonlinear function. Okay. So our goal is try to find a nonlinear function that captures the pattern of the data. I mean, if there is any, so this is also important. I mean, if our data is just white noise, then no, it's white noise. So, and this is our problem. And this problem, especially in high dimension and highly nonlinear, then neural network is very efficient in approximating this type of problem. And now let's try to see what a neural net is. So let me add the remark here. So remark. If n is large and the pattern is highly nonlinear, then, so in short, NN, neural network, is very good at fitting these data. So okay, so now let's see what NN is. So let me first draw a diagram. So let's suppose n equals 3. Okay. So our data have 3 components, which means x1, x2, x3. And something like, so I'm gonna draw a diagram. These 3 dots means 3 neurons. And we have 3 inputs. So x1, x2, and x3. So let me fix, I think I want to fix the notation previous here. So I want to fix this notation to be, I want to add this the ith data as a superscript. And then here we use subscript. Okay. So what happens is, so this is input layer. We have, let's say, 3 dots, and 1 dot corresponds to 1 neuron. So each dot corresponds to 1 neuron. Okay. And next, we have a name for the next. It's called a hidden layer. And let's say we have 2 neurons. So now each layer accepts the inputs from previous layer. So for example, we give these neurons a numbering. So for example, this is the first neuron in the input, second neuron in the input, third neuron in the input. And this is the first neuron in the hidden layer, the second neuron in the hidden layer. And lastly, for example, we have our output layer. And we just have 1 neuron, which is our model's output. So how does these neurons connect with one another is for each neuron in a layer except the input layer, it's connected to previous neuron by a linear relation composed with a nonlinear relation. So let me explain. For example, if we look at the first neuron at the first layer, or say layer 1, which is a hidden layer, it combines the input from all previous layers. Whoops. Okay. And then, let me give this name. And then it outputs something to the next layer. So now let's write down the mathematical formula to describe this. Okay. Let's say we have Z1. Okay. So we have Z1 here. And then what happens is Z1 equals the linear combination of the input from previous layer. So for example, so we have an input from the first neuron, then it multiplies with a weight. So the weight is subscripted in the following way. So I'm gonna first write down the subscript and then I'll explain how we give or assign these subscript. So this is 1, 1. This is W 1, 2. Oops. And this is W 1. So D1 equals W11 times X1 plus W12 times X2 and plus W13 times X3. Okay. So what happens here is now let's explain the subscript. So we have two subscripts. The first subscripts of these W, so right here, W11, W12, and W13. The first subscript, the subscript that's nearer to the input. So for example, this represents, so this one right here, so this one right here is corresponds to the first neuron in the previous layer. Okay. And this one right here, let me use another color. So this one right here is the first neuron in the current layer. Okay. So similarly, we can see that. So for example, this W12 here corresponds to this 2. So let me add. And this 3 here corresponds to this 3. And we have this 1 here corresponds to this 1. So now Z1 is a linear combination of all previous input, okay? And now Z1 is gonna feed something to the next layer. So when we, after this linear combination, so we'll apply a nonlinear function on Z1. So, and it generates the output of this neuron. So now let's recap. The input of this neuron is a linear combination of all the neurons from previous layer, okay? And after we get some number, this linear combination, this number is go through some non-linear function sigma. And now let me define sigma. So sigma doesn't have any subscript. Normally we just choose the same sigma in the same model. So sigma is called an activation function. Oops. All right. So, and it's a nonlinear function, and sigma has to be a nonlinear function. So in the breakthrough of the machine learning in the 21st century, the most used sigma is called the ReLU function. So ReLU is R-E-L-U, and it stands for so ReLU stands for rectified linear unit. Okay. Its definition is pretty simple. Even though it's nonlinear, but it's a continuous function. That is, when x is greater than 0, it's just x. Okay. So when x is less than or equal to 0, it's 0. So if we plot this function, I mean, it looks pretty simple. So this is x, and this is sigma x. So when x is greater than 0, we have this is x. And when x is less than 0, we have it is 0. So it looks like this. Let me use this code. Okay. So this is ReLU of x. All right. And first of all, it's nonlinear because the linear function in 1D has to be a straight line. Okay, so this is the nonlinearity. And this function is also not differentiable. But in the homework, we'll learn ReLU is called weakly differentiable. So in the homework, you are asked to verify some like weak derivatives definition. So that's some problem in our first homework. And so this is a ReLU function. So how the ReLU function is used is we put this ReLU function here. Okay. So this neuron accepts input from here, here, and here. And what happens is after we have this linear combination, it goes through this nonlinear function and we get a 1. So what does this ReLU does is it filters the signal. So later we will see when we demonstrate the model. So what does ReLU do? So what does ReLU do is filtering of the signals. Okay. And now let's back to the model. And now we can write down the full formula, which is A1 equals sigma of a vector W. So W equals, and let's give this W1, okay, and dot product with our input X. So our X is X1, X2, X3 transpose. Okay. So now let's look at the other neuron. and this neuron is Z2. All right. And we can write down something very similar. So I'm gonna plot this diagram here. So this is Z2. And we have, I forgot what color I used. Okay, orange. So X1, X2, X3. And we have something like this. And we have Z2 is very similar. Our naming is W21, W22, and W23. So what we have here is Z2 is W21 times X1 plus W22 times X2 plus W23 times X3. And similarly, in the output of the hidden layer to the output layer, we add a nonlinear function to it. So this is A2 equals sigma of Z2. So, and we write down this, explicitly. Then it is A2 equals sigma of Z2, which we rewrite this one as an inner product. So it's going to be W vector 2 dot product with X vector. Okay. And finally, what we do is, if we look at the last layer, so what do we have here is A1 and A2. So we look at our final output, which is our y hat. Okay. So then it is just, let me still use this. Okay. So then we can have, it's still a linear combination. So we use y equals u1 times a1 plus u2 times a2. Okay. And what we have is, this is u dot a vector. So where a vector is a1, a2 transpose. To capture, okay, so to recap y hat, our model's output is y equals, okay. So here, because we do not know like y is greater than 0, less than 0, so we don't have to add activation function in the final output. But y basically equals u dot with a, and this is u dot with sigma of z. So, and I do want to mention sigma z is nothing but sigma z1 and sigma z2 transpose. So that this notation means component-wise. And now we can write it even more. So we have, this is, and z is z1, z2, right? So, so it's sigma z1, sigma z2 transpose. And we expand even more. We have, this is w1 dot with x and sigma w2 dot with x. Okay. So this is a fully expanded model of our first neural network. And this is a model. So it's a highly nonlinear function. And the next thing, okay, the next thing I want to talk about here is bias. So whether to add bias. So the question is when to add bias. I mean, if we look at our model right here, so at each layer, for example, Z2, if it's a linear combination of all previous like input, it is possible that for the true ground truth model, it is possible that all of these are 0, but we have something non-zero. So that is called the bias in the neural network. And to incorporate this type of bias, we need to add a bias number for each neuron. So when to add bias is when X and Y have a non-zero mean. So for example, for our data, we have a collection of highly nonlinear, high-dimensional data. Okay. So if the average of this and this, the mean is not 0. So for example, the mean of xi is not 0, and the mean of yi is not 0, then we have to include a bias in our model. Then bias needs to be added in our model. So, I mean, the inclusion of bias is pretty straightforward. So let's recap what we had. So we had x1, x2, x3, okay? And we have z1. So we have w11, w12, and w13. And z1 equals w11 x1 plus w12 x2 plus w13 x3. To include the bias, we simply add a bias number here. So this is a bias. Okay. Sometimes we don't have to, but most of the time we have to. So if the data is normalized and it's very good, we don't have to. And including the bias actually makes the model not unbiased, which is not good in terms of statistics. But sometimes we have to add it. So, and this is the bias. So this is our model. And similarly, A1 is sigma of Z1, okay? So this is where to add bias. And similarly, we have to add bias for Z2. So for example, Z2 here, and Z2 is also W2 dot product with X plus a bias, which is B2. Bias for the second neuron in the hidden layer. And similarly, in the last layer, so we have the activation, A1, A2, and our final output, which is y hat. So y hat will be u vector dot with a vector. So u1, a1 plus another c1. Okay, so u2 times a2 plus c1. And this c1 here is bias. So this is how we add bias. If our model is unbiased, we don't have to, but most of the time we have to. Now let's look at how to simplify notation. So okay. And now let's draw this picture again. So we have x1, x2, x3, and we have z1 and z2. Okay. Let's think about the unbiased case. Okay, so no bias. Z1 is a linear combination of these three neurons. And Z2 is a linear combination of the value from these three input neurons. So if we write down Z1, Z2, so Z1 is basically, so this is X vector, and this is W11, W12, and W13, okay? And now let's look at Z2. Z2 is another vector, W, which is W12, W22, and W23. Okay. And now we want to combine them together. That is, we have Z1 vector, so we have Z1 vector and Z2 vector is we have a matrix that is W11, W12, W13, and W12, W22, and W23. I think somewhere I made it wrong, right? This should be W21, my bad. Yeah. Okay. I mean, this is exactly a matrix numbering, right? So, oh, sorry, I forgot to put this. And this is exactly the matrix vector multiplication. So we have a 1 by 2 vector, okay? And we have a 2 by 3 matrix. And this we have a 2 by 1 vector. So 2 row by 1 vector. And we have a 3 by 1 vector. So a 2 by 3 matrix multiply a 3 by 1 vector, we get a 2 by 1 vector. So this is how we simplify the notation. Is we simplify it as Z vector equals a W matrix multiply with X, and W matrix equals Wij, which is this is called a weight matrix. Right? So sorry for you guys listen to me babbling for 40 minutes. I forgot to do this poll. Let me just do some sanity check, see if everyone is following. Maybe you have lost, or you may have seen this material before, or you know, but not in the linear algebra way of presentation. So here I want to present this material. Thank you guys. Okay. Here I want to present this material in a more linear algebraic fashion. And so this is our weight matrix, and we simplify our notation in this way. And then even more simplify is our activation is then, so activations from the hidden layer is then A equals sigma of W x vector. Okay. So finally, this is our model. So model function. So model function is H, which is defined as the U vector and time this nonlinear function. And I want to emphasize, so the U vector and the W matrix are the parameter of our model. Okay. So this is the model. Next step is loss function. So loss function. Like we learned in the last lecture, the loss function characterizes one thing. It characterizes the output. It characterizes the difference of the output of the model to the ground truth. Okay. So I believe if you have taken 449 and in our final review, and of course as well as our final exam, so we'll see something like this, which is called least square. So we compute this thing, that is, we compute the difference between y hat and y. So if y hat is a scalar, and then it is just absolute value. So then this is just absolute value. Okay. So for example, if we write this explicitly, then it is u dot sigma of w multiplied with x subtract y square. Okay, so this is our loss function for one datum and for one data point. If we have multiple data points, so if we have xi and yi, and for I from 1 till capital N, it means we have capital N data points, then the loss function is the summation of Li, and it is, we just added these up, okay? We just add these up. So what we have is u dot with sigma wx the ith data subtract the ith y. Okay. So this is our loss function, and sometimes we take average, and sometimes we don't have to take average. It's totally up to you. But this is our loss function. So in next lecture, So we'll derive explicitly how do we take derivative and how do we apply gradient descent to this loss function. And on Friday, we'll have a coding lecture, which I'll demonstrate explicitly how do we play with the PyTorch, the modules, and how do we implement a neural network explicitly, like not just calling some functions, but implement in PyTorch from scratch of how do we code a neural network we just learned from now. So the requirement is I'm gonna use a Google Colab. So of course, if you wanna follow me, implementing this in PyTorch, you need to have a Google account. So if you don't have one, it's time to get a Google account. So that's it for today. So I'm gonna leave here for a few minutes. I'm gonna stop the recording. So if you have questions, you can stay.